So for the second common applications, we have here exponential decay by half-life. So decay by half-life, what does that mean? So population decay by half-life of radioactive substance is the time it takes for half the substance to decay, meaning the whole substance population will be reduced by half at a certain time. That is the half-life. So how are we going to apply this in exponential function? So again, we are in exponential decay by half-life. So now if the half-life of the substance is t units, that is the time, and y sub 0 is the amount of the substance corresponding to t is equals to 0, or the initial amount of the substance, then the amount y, or the future amount of substance remaining after t units of time is given by y is equals to y sub 0 times 1/2 raised to t over capital T. So in here, this value will be the remaining substance, the y, and our y sub 0 here is the initial substance value, or amount of the substance, and 1/2 here means half-life. So we are going to raise that to t, wherein the time that you are going to compute the remaining substance over the t, that is the time of half-life, the capital T. So now let's have an example.
So given this problem, we have supposed that the half-life of a certain radioactive substance is 10 days and there are 20 grams initially. Determine the amount of substance after 40 days. And also give the exponential model for the amount of the remaining substance for the certain time. So first, for our solution, let's find the given values. So we have here the half-life. What is that? That is T. So that is 10 days. So in here, our T is the half-life. In our previous application, which is doubling your T, is the time when your amount will double. So in here, this is the time when it will have to be reduced in half. Now, another given, we have initial value, which is y sub 0, which is 20 grams. Now, we have to determine the amount of substance after 40 days. So, let's try first to get if your T0, so 0 days, your Y is equals to 20 grams. So initially that is just 20. What about if it's 10 days? So if your time is 10 days, so given that you will have a half-life. So meaning you are going to multiply your initial value to 1/2. What if it's the time doubles? So you have 20 days. So your Y now, the amount of the remaining substance will be 20 times 1/2. And since your time doubles, so because 10 times 2, that is 20. So you will still multiply your value to 1/2. Now, let's have for 30 days. So this time, the amount of substance will be multiplied to thrice with 1/2. So we have here 20 We have here 20 times 1/2. We have here 20 times 1/2. So since it's you're just multiplying it to itself twice, so that is raised to 2. What about this? So we have 20 times 1/2. So we have 1, 2, 3. So that is 3 raised to 3. The exponent is 3. What about if it's 40 days? So we are asked to determine the amount of substance after 40 days. So our y will be 20 times, so 40 divide 10, that is 4. So you have 4 times that is reduced into halves. So we have 1/2 times 1/2 times 1/2 times 1/2. So we have 20 times 1/2 raised to 4. This is equals to 1.25 grams. So on 40 days, after 40 days, you will have a remaining substance which is 1.25 grams of bacteria. Of radioactive substance rather. Now, let's define the exponential model of the function which is the remaining substance. So this time, you have y of t. So a function of t, that is, you have the initial substance, y sub 0 times, you have a constant 1/2 because that means you are reducing it into its half-life. Then you have your t, given t, remaining days, number of days, divide to your half-life. That is your given half-life. So, let's substitute our given. We have y of t equals to 20 grams times 1/2. So, your function now is t here. Then, divide to the constant 10, which is the half-life 10 days. So this is our exponential function for the amount of the remaining substance.